So we radically change topic and we go back to routing. So far we've seen routing inside one domain, and now we will see routing globally in the internet. And what is illustrating is that the internet is not managed. There is no internet organization that runs the internet. There is an organization that runs the standards of the internet, how TCP should be, but nobody checks whether your TCP is how TCP should be. We just believe TCP is deployed by Google, Apple, Microsoft, so those people are serious, they do their own thing, but nobody runs the internet. The numbers are allocated, the IP addresses, the port numbers are managed, at least for the reserved ones. But how routing occurs between Swisscom and AT&T, for example, is the business of Swisscom and AT&T. In other words, the global internet is self-organized, which this cartoon is trying to illustrate. So the topic is interdomain routing, which is the routing between domains. Inside every domain, inside the domain you have a management and things are well organized by hierarchy. Between domains, we need to do something. So the first thing to observe is there is not a unique routing protocol that runs everything at every level. There is one called BGP that runs only the interaction between domains. Inside the domain, we can use one routing protocol, RIP or EIGRP. Inside another domain, we can use OSPF. So each domain will use locally its own routing method. Globally, between domains, we will use only one method, always the same, only one protocol, which is called BGP. A bit of terminology. BGP is called exterior routing. Exterior because it's between domain. So because nobody is running the global thing, it's considered exterior because for anybody running a network, BGP has to do with the things outside this network. The routing protocol we've seen so far are called interior routing protocol. So an interior routing protocol, now the old internet terminology is gateway protocol. Gateway is the old word for router. So an IGP means a routing protocol for a single domain. RIP is an IGP, OSPF is an IGP, EIGRP is an IGP. Sometimes people call EGP an exterior routing protocol, but there's no need for a generic name because there is only one exterior routing protocol. It's called BGP. There's only one that's deployed and running in the internet. Of course, academics have infinite creativity, so lots of people have invented exterior routing protocol, but they are not deployed. There are many people who are in favor of deploying IDRP one day, but it still is BGP running. Right? Deploying something new is very difficult. We are seeing that with IPv6. I mean, IPv6 was invented 20 years ago. It is still practically not deployed. So moving from IPv4 to IPv6 is a problem because IP is global. Similar, BGP is really the glue between all elements of the internet, so modifying it is very difficult. Some terminology. ARD is practically taken as a synonym for AS. AS means autonomous system. It means a domain. That's the domain name in the context of BGP. ARD means the same practically for everyone except for the purists, where an AS is an ARD that has an AS number. So what is an AS number? Well, the domains have numbers which have nothing to do with IP addresses. They are domain numbers. For example, 559, if I remember well, is switch. Yes. So that is the name, or that's the number that is used to uniquely identify a domain in the internet that is called switch. EPFL is also an autonomous system, but it doesn't have a number. Why doesn't it have a number? It could have a number, but for a long period of time, numbers were AS numbers. Before they were originally 16 bits, then they moved to 32 bits. Before they moved to 32 bits, there were not so many numbers, so we tried to save them as much as possible. And because EPFL is never a transit network, it's always receiving internet service from switch or from others, so it's never transit. And if you're not transit, you don't need a number. We will see why a bit later. How do BGP and the interior routing protocol interact? Well, this is showing here 4 domains, each with their, perhaps with their AS number, if they have one number. So inside the domain, there is RIP, like we've seen, that's familiar for us. When we will talk about OSPF towards the end of the course, we will see that inside the domain, you can subdivide the domain into subdomains. OSPF allows you to do that, but that's a detail we can ignore. And then between the domains, we will use the BGP version 4, which is the only version used today. Now, what we see is that there are no BGP routers that would be outside of the domains and would run the domains like one could perhaps expect. Instead, BGP is run on routers, the same routers that run also the interior routing protocol. They also run BGP, and they talk across the domain boundary to other routers that also run BGP. So for example, here we have A2, D6, D5, D2, C1, C4, B2, and B4. Those are all the routers that run BGP. There might be more, as we will see, but at least those routers have to run BGP. BGP handles both IPv4 and IPv6. We will see that in Lab 6. And BGP uses a method of routing that's not distance vector, is not link state, it's called path vector. So it's similar to distance vector in the mechanics, but it uses a complete enumeration of the path that I will explain now. So this is showing how domain A, perhaps one router at each boundary here, speaks to the rest of the world so that the rest of the world discovers how to route to prefixes N1 and N2. A will send to B and C routing advertisements that will contain the prefixes, this is like with distance vector, plus the path, which is just A in this case. B receives that from A, it will forward it to all its neighbors, in this case it forwards it to E, and it will append itself. So at the end, E will have received through this and through that, it will have received information about N1 and N2. That will be this one, for example, it will have received a path BA N1 and another path DCA N1. So E will have received 2 advertisements. If we compare to distance vector, in distance vector, what we would have is instead of having the complete list, we would have just the distance, number of hops, for example. We would have distance 3 and 1. Here we have the complete path. And then E will apply its decision process and will pick whatever it prefers according to its own rules. Here, in this case, E has preferred this one, perhaps because it prefers paths that have the smaller number of autonomous systems of AS in the path description, or perhaps because E does not like C. E doesn't want to go to N1 and 2 via C. Those are things that are possible if we do path vector routing instead of complete distances. And this is where we will stop for today.